All right, today we are going to talk about Gauss's law. Gauss's law is the first of the four Maxwell equations that you're going to encounter in this class. This is a law that relates the electric field to the charge. You can kind of think of this as an integral form of Coulomb's law. It's relating electric field and charge, and we've seen that sort of thing before for point charges. The person that is credited to coming up with Gauss's law is Carl Friedrich Gauss in 1813, and there is some discussion about the fact that maybe he wasn't the first one that came up with it. Nevertheless, he got the credit for it. There are, well, first of all, let me just jump in and show you what Gauss's law looks like mathematically speaking. Mathematically speaking, Gauss's law is this: the closed integral E dot dA is equal to Q enclosed divided by epsilon naught. Okay, that's Gauss's law. Now don't worry too much if you don't know what the symbols mean just yet. We'll go over each one of those. There are, however, before we dive into this, a couple of things that you need to know. And let's talk about those things. The first one is this concept called a Gaussian surface. Gaussian surfaces play an important role in understanding Gauss's law. First of all, in a Gaussian surface, you can think of that as an imaginary three-dimensional surface. Now, it's imaginary in the same sense that the equator is imaginary. The equator, there's not a physical line drawn where the equator is. Nevertheless, the equator is a real thing because you know it's halfway between the poles of a rotating sphere like the Earth. Nevertheless, you can think of the equator as an imaginary line. In the same sense, you can think of a Gaussian surface as an imaginary surface. It could be real, but it's imagined because you get to come up with whatever shape of Gaussian surface you want. Now, there's a couple of things about the Gaussian surface that are important. First of all, it must be a closed surface. Now, closed surfaces are things that, well, there are a limited number of closed surfaces that have nice mathematical functions to describe their geometry. For example, a sphere. A sphere, you can determine the volume of a sphere or the surface area of a sphere pretty easily. The same with a cylinder, same with a cube, maybe a pyramid you can do that with. But there are a limited number of cases that you can probably think of and solve for surface area explicitly. Now, for this imagined Gaussian surface, it's going to be 3D, it's going to be a closed surface. So as you can imagine, there's probably going to be a limited number of cases where the geometry is going to allow us to get explicit solutions using Gauss's law. So the shape of the Gaussian surface can technically be any shape. You know, it could be a nice round sphere, or it could be something, you know, weird shaped like that. Either one of those are allowed by Gauss's law, as long as it is a closed three-dimensional surface. But this one is going to be more useful than this one. And the reason is because this one we can calculate its volume, we can calculate its surface area without much trouble. This one we'd have more trouble doing that. Nevertheless, Gauss's law doesn't require a nice geometry. It will work with anything. Okay, it's going to be something that we're going to put a charge inside of, and you'll see how that works later on. That's the idea. We put a charge inside the Gaussian surface, and then we're going to relate the electric field. Let's say we put a positive charge here. We're going to relate the electric field lines that pass through that imagined surface. The electric field lines that pass through that to the interior charge that's inside of it. Now that kind of makes sense if you'll stop and think about it. The electric field lines that come off of this are definitely going to be related to the amount of charge that's on the inside. So that brings us really to the second thing that we need to discuss before we dive into Gauss's law, and that is this idea of flux, specifically electric flux, because we're talking about electric fields here. The flux tells us how much electric field passes through a surface. So let's say we've got electric field lines that go in that direction right there. And that is the electric field. Now let's say we've got a surface. Now, I'm not going to talk about a closed surface just yet. This is just any surface whatsoever. So let's draw a surface here. Let's give it some dimensionality. So it's got some thickness there. Okay, that surface has some area, and you can imagine this is the front-facing area here. And that area right there, you may have seen this before in your previous physics career, that you can symbolize that area as a vector. And that vector is normal to the surface. So if this had been a small flat surface, that vector would be pointing perpendicular to the surface or normal to the surface. And the magnitude of that vector is the surface area itself. So we call that the area vector. All right, as you can imagine here, you could take this electric field and break it up into components. One of those components could be in this direction, and the other component could be perpendicular to that direction, which may be down like this. Okay, so you could take each one of these electric field lines and break it up into components. Well, which component is which here? If you'll think about the angle between A and E, then that's this angle right here. That's the angle between A and E. We'll call that theta. All right, well, if we break up these electric field lines into components, then one of those components is parallel to A. In other words, it's in the same direction as A. It's normal to the surface as well. And the other one is along the flat of the surface here. So it's along the surface. This one is in the direction of A. So this is the E cosine theta component of the electric field. That's just this vector right here. All right. So flux, what is flux then? Flux is the component of the electric field that's parallel to the surface vector multiplied by the surface vector. Now, that is given a symbol, capital Phi, for flux. That's what flux is. Flux, in this simple case right here, is just E times the cosine of theta. That's the component that is parallel to the surface vector multiplied by the surface vector itself. So the units are going to be, let's see, newtons per coulomb. That's the electric field. Cosine theta doesn't have units, so the A is meter squared. So Newton meter squared per coulomb is the proper unit for flux then. All right. Well, this E cosine theta, this is what you get if you take a dot product. So if you did E dot A, took the dot product of the two vectors, that's the flux. The flux itself is a scalar. It is not a vector. And that's what you get when you take the dot product of two vectors. You get out a scalar quantity here. So that's the generic form of a real simple flux. Okay? Now, if we had a closed surface, then what's happening is we would be able to divide it up into tiny little areas. So let's say we had a closed surface that's in the shape of a sphere. You can imagine the area being the sum of a bunch of little squares. So those squares are small, they go all the way around the surface here. And imagine those little squares being as small as you want, and the sum of all of those individual squares then would be the surface area. So another way to sum up the surface area is this. You sum up around the whole surface. Now, this is a closed surface, so that circle there means that this is a closed surface. If you ever see that, you're dealing with a three-dimensional closed surface. The dA vectors, that would be the little dAs coming off of each one of these. So that would be a dA. There would be another dA coming out this way. And those dA vectors would point radially outward. For every little square, it would be normal to the surface, just like this is normal to the surface here. Now, if you summed up all of those dA vectors, then what do you get? You get the surface area of your three-dimensional closed surface, whatever that happens to be. So if you want to know what the flux is through a closed surface, it's going to look like this. Flux equals the integral of the closed surface multiplied by this, E dot dA. Okay, so there is the flux equation. Now, if you'll look back up here at Gauss's law, you can see that that's the left-hand portion of Gauss's law. So we could say flux, electric flux, equals to Q, and that's Q enclosed. That's a subscript ENC, which is an abbreviation for enclosed. Q enclosed divided by epsilon naught. So that's this portion right here is the left-hand portion of Gauss's law. And that's also our definition of flux. Now, to be honest, a true definition of flux doesn't necessarily require that the surface be closed. So flux in and of itself is just E dot dA. That's a much better definition of flux itself. But for our purposes here, we're going to have closed surfaces. So the little circle on the integral sign indicates that we're talking about a three-dimensional closed surface. Flux itself, not necessarily closed. So. All right, we've talked about flux. Let's use it, and let me show you how we might use it in an equation to solve a simple problem. Now, let's say we've got electric field lines that are heading in that direction, like that. Okay, so we've got a nice constant continuous electric flux here. And now let's put a cylinder in here. Cylinder is a closed three-dimensional surface. So let's line the cylinder up in such a way that it's parallel to the electric field lines. And those are the two ends. You know, one of those is going to be behind. So we'll put a dashed line to indicate that that's behind. All right, this cylinder, let's say, has a radius. Let's give it a nice R, capital R, for the radius here. And whatever this is down here on this end, it's the same on this end. So this is a nice right cylinder, nice and square. Okay, if you look at this, there's no charge inside the cylinder, but there is an electric field that's passing through the cylinder. Now, if you had to estimate the flux, you can probably already guess what the value of the flux is. The amount of electric field going into the cylinder on one end is equal to the amount of electric field coming out on the other end. So if you summed up the total electric field here, the total electric flux here, you would say, well, there's just as much going in as there is coming out. So if we call what's going in positive and what's coming out negative, then the sum total of all of the electric flux is going to be 0. And you would be correct. You have just as many field lines going in as you do coming out. Now you notice it's really what's happening here at the ends that matter, because the electric flux is going in on this end, coming out on that end, and what's happening here on the sides doesn't really matter. It's not like the electric flux, because of this nice uniform electric field we have, it's not like there's any flux coming out the sides here in any direction. All right, so if that's the case, then we should have flux equal 0. Now that's what you're anticipating. Let's use the flux equation and let's see if that's the case. Okay, specifically, flux equals the closed integral, because this is our closed cylinder here, of E dot dA. All right, now we've got a cylinder here. You know how to figure out the surface area of a cylinder. First of all, this central part here, let's label the parts. Let's call this end 1, the middle section 2, and this end down here is going to be 3. So that's 3 right there. All right, so this 2 area, area 2, you can think of that as a soup can, or a Pringles can in this case, because I've drawn it so long. So how do you do that? Well, if you knew this length right here, let's say that's L, and the surface area of that central region is just going to be L times the circumference of the circle, which is 2 pi r. So that's going to be the surface area of the central region, area 2. The surface area of area 1 is just pi r squared. And then you're going to have that on the other end as well, like that. So what is that? You sum all of those together, and you've got the total surface area of our Pringles can then. Now, how did you do that? Well, the way you did that was you broke up the area into 3 distinct parts. And those 3 distinct parts, you were able to calculate the surface area of each part relatively easily. And then in the end, you just sum them up. That's going to be the same thing we're going to have to do here. So this E dot dA, that's the electric field over the whole surface area of the closed surface. So if I break this closed surface integral up, I can break it up into the integral over area 1 of E dot dA plus the integral over area 2 E dot dA plus the integral over area 3 E dot dA. And that's the total flux. Okay, so if we evaluate these 3 integrals here, and this sum them together the same way that we did for surface area here, then we'll have the total flux. So let's break it up and let's do each one of these individually. So let's start now with area 1. If we look at area 1, let's zoom in on it here. There it is right there. Well, the area vectors, in fact, remember the way that you determine an area is you break it up into little tiny pieces and you sum up all the dA vectors. But for each one of those, since this is a flat surface, the dA vectors are going to point normal to the surface. Regardless of which dA I pick that one there, same direction. All of the dA vectors point in the same direction. Remember, a vector has a magnitude and a direction. It does not have a position. So each one of those is the same vector, really. All right, that's the direction of the area vectors. What about the direction of the electric field? Well, here in area 1, the electric field is directed that way. So the E vectors point that way. And that's true no matter where you're at on that surface. So even though I just drew one field line going through it, that's really just for convenience. All of the electric field lines in this area go in that same direction there. Okay, now noticing that is going to allow us to solve this one integral, this area 1 integral. So the integral over area 1 of E dot dA, that's a dot product, so let's break apart the dot product. That's E cosine theta dA. Now the theta is the angle between the E and the dA vectors. The dA vectors, you know the direction for that, you know the direction for E, and we've chosen our geometry in such a way here that that's always going to be the case. The angle between the dA and the E is 180 degrees. And that's always the case on surface area 1. No matter which dA vector you pick, that's going to be the direction associated with it. So if theta is 180 degrees, then what's the cosine of theta? The cosine of theta is going to be -1. And that -1 is going to be the same over surface area 1. So as long as we're talking about surface area 1 and surface area 1 alone, then this is a constant. The cosine of theta is -1. That means we could factor that out of the integral. We could also factor out this E. Now, why is that? Well, because of the nature of the electric field. The electric field lines, the way that we set it up, are constant and uniform in this whole area. So the electric field at that point is the same as that point, is the same as this point, that point, or any point you pick, the electric field is exactly the same. The magnitude and the direction of the electric field is the same anywhere in this area. Okay? So the E is constant. So let's factor out the E. Let's factor out the cosine theta. Remember, that's going to be -1. And what have we got left? The integral of area 1 dA. Now, rather than go through the steps of evaluating this, just think about what that integral is. That integral is surface area of area 1. You know what that surface area is. It's a nice circle. Since that area is a nice circle, then you can just write minus E, and we'll jump straight to the solution here. This isn't a math class, so you don't have to go about evaluating that integral. It's just pi big R squared. When we get to this point here, we have evaluated that whole portion right there, the first portion over area 1. All right, let's do the same thing for area 2 now. For area 2, that's the central part of the Pringles can. So here's the Pringles can, and now it's got open ends. The ends are open. We're not worrying about the ends, just over area 2 here. We know that length. We could say we know that length. You're going to discover here in a second that it's unimportant what that length is. But in this case, remember the electric field lines are going in that direction all the way through. Now that should be parallel, but those lines should also be parallel with the edge of the Pringles can here. All right, so where do the dA vectors point? Well, remember, to sum this up, you break it up into little pieces, sum up the dA vectors, and then you've got the total surface area. But the dA vectors point in different directions. So at one point, the dA vectors point that way. But remember, this is three-dimensional, so you got the dA vectors pointing that way. But then as you rotate, you got the dA vector pointing that way, dA vector pointing that way, dA vector pointing that way, and that way. So you're going to have all of these various angles for the dA vectors, and you have to kind of imagine that as being three-dimensional, that are normal to the surface. So the dA points that way, dA points that way, that way, that way. But if that's the case, what is the angle between E, which goes into the surface and passes through the central region, and the dA vectors? Well, if you'll think about it, the angle theta is always 90 degrees for area 2. That's the angle between the E and the dA. So if we try to evaluate this integral over area 2, E dot dA, that's equal to the integral over area 2, E cosine theta dA. So for all of area 2, the angle is 90 degrees. And what's the cosine of 90 degrees? Well, it's going to be 0. So this is going to sum up integral E dot dA over area 2 is 0. All right, then for area 3. Area 3 is pretty much the same as area 1, but it's at the other end of our Pringles can. So if I draw area 3 here, the dA vectors, regardless of where you're at on the surface, is going to point that way. The E vectors also are going to point that way. So if the dA vectors and the E vectors, and that's true for every point on the surface here, at every point on the surface, the angle theta is going to be 0 degrees. So with that information, let's evaluate the integral over surface area 3, E dot dA is equal to, let's go ahead and break apart the dot product, E cosine theta dA. We're integrating just over area 3. The cosine of theta is going to be 1, since theta is 0 degrees, all over the surface, so it's going to be constant, it's just 1. The E is also constant, so we can factor it out of the integral because it's exactly the same value at every point on surface area 3. So this reduces down to E times the integral over area 3 of all the dA vectors. And what is the sum of all the dA? Well, that's just the surface area, E pi r squared. So the total flux here, if we go back up here, the total flux is for area 1 minus E pi r squared, plus for area 2, plus for area 3, sum all of those up, what do you get? Exactly what you expected. The grand total, the total net flux through this cylinder is 0. And why did we expect that? Because we have just as much electric field going in one end as we do coming out the other. And you notice the electric field, none of it comes out the sides, and that's what you see. The flux through the sides is 0. So there you have it. We've done an example here of not Gauss's law, but a computation of the flux. And the flux portion of Gauss's law is probably the most difficult part for students to grasp, at least initially. All right, let me quiz you a little bit then. We could write Gauss's law this way. We haven't really talked about the right-hand side of the equation just yet. Or we could write it this way. Closed integral E dot dA equals Q enclosed divided by epsilon naught. But now let's talk about the right-hand side here. The Q enclosed, I keep calling it Q enclosed, but enclosed in what, do you think? And the answer is inside a Gaussian surface. The Gaussian surface that you get to create. But Q enclosed is total net charge. So it's the sum of all of the charges that are inside of the Gaussian surface. We'll work examples later and hopefully it'll become clearer. But for right now, just notice that Q, it can be positive, it can be negative, or it could be 0. If it's 0, then what's the flux going to be? 0. Okay, so the sign of Q, that's the amount of charge that's enclosed inside your Gaussian surface, is going to determine the direction of the net flux. Remember, the left-hand portion here is the total flux. So whether or not the flux is outward, which would be positive, or the flux is inward, which would be negative, then the sign of Q enclosed is going to help us determine that. Let me remind you, back here we had flux going in, the electric flux is going into surface area 1, and we had a negative flux. When the flux was going out, when the electric field lines were going out, then we had a positive value for the flux. So positive means outward, negative means inward as far as the flux is concerned. So the sign of the charge helps determine the flux value, whether it's going inward or outward. So let me quiz you a little bit then. Let's say that we have a dipole here. We've got plus, minus, plus Q, minus Q. And the electric field lines for such a dipole are going to look something like this. They're going to have a direction associated with them. It's always going to go from the positive to the negative charge, except for this one that goes off that direction, this one that comes in from that direction. All right, now, given that we have electric field lines all the way around, I want to ask you a question. Let's say that I imagined a Gaussian surface as a sphere, and that sphere surrounds this charge up here. So surface 1 is what I'm going to call that. That's surface 1. All right, surface 1 right there. The flux is what? Well, we can say a few things about the flux. First of all, it's all outward. If it's all outward, what's the sign going to be? It's positive. It's so because we are enclosing a positive charge here, the net flux is outward. It is all leaving the Gaussian surface. All right, let's pick another one. Pick another surface here. Let's say I pick a nice sphere around the negative charge, just the negative charge. Let's call that surface 2. Well, what can we say about that? The flux is inward because the electric field lines are going in through my Gaussian surface that I've chosen here. They're always going in. There are none that are coming out. This is going in, that's going in. So all of the electric field lines are going inward. What can we say? We have a negative flux. And the reason we have a negative flux is because my Gaussian surface is only enclosing a negative charge. Let's pick another example. Let's say I put right out here. I move my Gaussian surface, and now it's out there at position 3. Well, now what can you say about that? Well, the flux is 0. So the flux is 0. If the flux is 0, then you've got just as many field lines going in as you do coming out. Regardless of how I draw the field lines here, they're always going to go in this nice curved pattern from positive to negative. So if I draw lines going into that surface, then those same lines are coming out of the surface. So the net flux is 0. Well, what is the sign of the charge that's enclosed? Well, there is no charge. So the total enclosed charge is 0. All right, let's do one more surface. One more. This time, here's my Gaussian surface. You could say that's a nice sphere, but you get the point. It's not anything special about the shape of the surface. That's surface area 4, though. What is the flux? Well, if you look at it here, the electric field lines that are going out up there are coming in down here. And that's true of every point on the surface. Going out, coming in, going out, coming in. In other words, the flux that happens to be positive going outward is equal to the amount of flux that's negative going inward. So what do you expect the total flux to be? 0. All right. What's the net enclosed charge then? Well, you have to sum up the total charge that's inside the Gaussian surface. Now, it doesn't matter where that charge is inside the surface. All that matters is what is the net total charge inside the surface. And you see there's plus Q, minus Q. So the net enclosed charge is 0. Now you're starting to see perhaps what Gauss's law is really talking about here. This is the flux on the left-hand side, which has to do with the field lines that are leaving, is equal to the amount of charge, the net charge that's enclosed inside your Gaussian surface divided by epsilon naught. All right, I think it might be easier to understand if we do a problem, an example. So let's say I have a positive point charge, and that positive point charge is just Q. We could give it a subscript, Q naught, if you want to. All right, I'm going to use Gauss's law then, and this is the real power of Gauss's law, the real usefulness that you will use during this course, is to determine the electric field due to that point charge. Now, you know the answer to this. You already know that the electric field due to a point charge is 1 over 4 pi epsilon naught, that's K, Q, over the distance squared. So if I pick a point out here that is some distance, big R, away, then the electric field at that point due to this point charge is given by this equation. Okay, then how can we use Gauss's law to determine that? We know the answer, but Gauss's law ought to be able to tell us the answer. Well, the first step in doing something like that is to decide what your geometry needs to be. And how do you decide that? Well, the biggest helpful thing for determining Gauss's law is really your experience. So you need to practice these problems. Go ahead and make some mistakes. But it's obvious in this case, hopefully, that a nice sphere surrounding our charge, and the radius of that sphere is R, is a good choice for a Gaussian surface. Now, why? Well, consider Gauss's law here. Closed integral E dot dA equals Q enclosed over epsilon naught. When we break this dot product up, it becomes E cosine theta dA. What we want to be able to do is two things. First of all, we want the electric field at the surface to be a constant. If it's constant, then we can factor it out, and it becomes a lot easier problem. Also, we want this theta to be a constant, the cosine theta to be a constant, so that we can factor it out as well. So what we want to do is choose our geometry in such a way that the electric field is constant at the surface of our Gaussian surface, and cosine theta is constant at every point on the Gaussian surface. And if you'll think about that, the best way to do that is to take this point charge, put it in the middle of a Gaussian surface that is the shape of a sphere. Now you might say, well, what about other shapes? Why wouldn't a cube work? Well, if you'll think about that, if you had a cube, let's draw, there's the cube like that. The electric field is not going to be constant at every point on that surface because the distance here, the distance to that point, is farther away from the point charge than that point right there. Now that's not to say you couldn't use a cube, but your E is not going to be constant, so you can't factor it out. So you would have to perform an integral. First of all, you'd have to derive an equation for E itself, plug it in, and then do the integration to figure out what the flux is. The same with theta in that case. What about a cylinder? Same sort of thing. It may be the electric field is constant in one area, but it's not for the whole surface of a cylinder as well. The only geometry that gives us what we want, a constant E that we can factor out and a constant cosine theta that we can factor out, is a sphere. We make it radius R. We put the point charge in the center of the sphere. Okay, if we do that then, think about this. The dA vectors are on this surface. The dAs are always going to point radially away from the point charge. So over here, if I pick the dA there, points in that direction. You notice the dAs are not the same everywhere. Some of them point here, some of them point that way, and this is three-dimensional, so you're going to have some that point this way, that way, straight out of the sphere. So the dAs change all the way around. But remember, when you sum all of those up, you get the surface area. But what about the electric field? The cosine theta as well. The theta is the angle between the E and the dA. So we know the dAs are going to point every which way. Well, what about the electric field? Well, at that surface, the electric field also points outward like that. And that's going to be true at every point on the surface. Regardless of which direction you're talking about, the electric field lines point radially outward from the positive charge, and so do those dA vectors. So what does that mean? The cosine theta is a constant at every point on the surface, so it's going to be 1. And we'll just factor it out. Why is it 1? Because the angle between the E and the dA is 0 degrees. Cosine of 0 is going to be 1, and it is true for every point on the surface. Now, what about the E? The E is also constant at every point on the surface, and the reason it's constant is because we picked our Gaussian surface to be such that it is equidistant away from the point at every point on the surface itself. So the E is going to be constant. When I factor out the E, the cosine I also factor out, but it's just 1. What am I left with? Well, the closed integral of dA. This closed integral dA is the surface area of my Gaussian surface. So the surface area of this Gaussian surface, since this is a sphere, is going to be 4 pi r squared. And that's equal to, all right, we haven't talked about the right-hand side here, how much charge is enclosed. Well, I called this Q naught, so the total charge enclosed in my Gaussian surface is just Q naught. So this is Q naught over epsilon naught. Bring it down here, Q naught over epsilon naught. Okay, we've worked the left side of the equation, we've worked the right side of the equation, and we've gotten to a point now that we can solve for E, and that should be the last step here. Solve for E out of this, and notice what you get. You get 1 over 4 pi epsilon naught Q naught over r squared, which is the equation for the electric field of a point charge, right there. So if you were wondering at some point, why is it 4 pi? Why is it 1 over 4 pi? Where did that come from? You can see where it came from. It came from Gauss's law, from the symmetry of Gauss's law when you choose a spherical symmetry around a point charge. So that's where it came from the geometry. So there we've used Gauss's law to derive the electric field for a point charge, a distance r away from the point charge. Now, we can do some other things with Gauss's law as well, and you probably will in some of your homework, and we will work more problems here as well. But I want you to think about the case where we've talked about this before, where let's say I have some surface, and in this case we'll just say it's a nice three-dimensional closed surface. So, it's like a potato here. And it's a conductor. So here we've got this conductor. And let's say that the conductor is solid. And we put some positive charge on the conductor. Where's the positive charge going to move? Well, after a brief period of time, it's going to distribute itself on the surface. So on the surface of this solid chunk of metal here, like that, and because it's not uniform, you're probably going to have more positives at the sharp edges and the curves than you would the smooth areas. But that's beside the point here, because what I want to do is I want to figure out what the electric field is inside here. And let's get really close to the surface, and we'll draw a Gaussian surface then that's just right underneath the surface. So there's my Gaussian surface inside that chunk of metal. All right, Gauss's law, then closed integral E dot dA equals Q enclosed divided by epsilon naught. Now this is my surface. I imagine that, so because it's something that I created, an imaginary surface that I created, it's going to have some surface area. As far as we're concerned, it has an area. But notice the right-hand portion of Gauss's law is Q enclosed. Well, how much charge is enclosed? 0. There's no charge enclosed. Now, another way to say that is there's just as much positive as there is negative. So there's atoms inside my Gaussian surface, but nevertheless, just as many protons as there are electrons and this would be the case if all the charge lives on the outside. So, if that's the case, then this is what the closed integral E dot dA is. This is the flux. In other words, there's two ways that you could have this be 0. One is the area portion be 0. The other way is the electric field portion is 0. So for our example here, we've come up with a Gaussian surface. It does have some area, so the area is not 0. Therefore, the only conclusion that we can come to is on the interior of this conductor, the electric field is 0. And that's what we've talked about previously when we talked about how positive charge or any charge lives on the outside of the conductor. They set themselves up in such a way to produce an electric field that is 0 on the interior of the conductor. And that is true regardless of how close you get to the surface, as long as you are under the surface with your Gaussian surface here, your imagined Gaussian surface, then it doesn't really matter. The electric field is going to be 0. Even if you had something like this, even if you have, let's say we've got a cannonball and it's hollow and it's really thin here. So the interior here is hollowed out. Now we put positive charge on this. Where does the positive charge go? It goes to the surface. So if you had a Gaussian surface, imagine a Gaussian surface on the inside here, what's the flux going to be? Or what's the electric field going to be? The electric field is going to be 0 on the inside of that because there's no charge on the inside. There's no net charge. And that's true no matter where you're at. Even if you come here and place your Gaussian surface between that very thin shell, there's no net charge enclosed because all of the charge is going to run to the outside and distribute itself on the outside to try and get as far away from the other charges as possible. And since this is a conductor, it can do that. It can move. So a conductor is going to have charge on its exterior and the electric field on the inside of that conductor, regardless of if it's hollow or not, is going to be 0. All right, well, let's now consider the case of another conductor. And this conductor has a hollowed out region in the middle. And let's put some positive charge now on this conductor, and that positive charge runs to the outside here and distributes itself in such a way to create an electric field that's 0 on the inside. Now that makes sense just the way it made sense back here, that the positive charge is going to do that. Now let's do something a little different. Let's take a negative charge and let's put that in the center. No, let's make it positive. Let's just make it positive. Okay, now I have a positive charge that's in the center, and let's say that is plus Q, right there in the central region. Well, this is a conductor around here, so what could happen is that negative charges rush to the central region here and build up on there. Now, that negative charge, when you sum it all up, is going to be equal to the positive charge in magnitude, but opposite polarity. So if I've got plus Q at the center, then I'm going to have minus Q on that surface right there. Now that negative charge came from someplace. So we have an overabundance of electrons in the hollowed out center region that's been induced by the presence of that positive charge at the center. So where did those charges come from? That means there is a deficiency of electrons somewhere else. And that means we have positive charges out here in the sphere, but those positive charges are going to get away from each other as much as they can and create even more positive charge out here. Now what does that mean? That means we've got extra positive charge out here to make up for the fact that we've got this negative charge built up on the interior of the hollow wall. And the only reason that that charge is there is because we have a positive charge that's present at the center. Now, think about Gaussian surfaces. If I have a Gaussian surface, let me see if I can maybe make it a slightly different color. If I have a Gaussian surface, the Gaussian surface is in that hollowed out region and is enclosing only the positive charge. All right? Flux in that case is going to be positive. Why? Because I have a positive charge enclosed. Now let's think about a Gaussian surface in that region there. That's on the Gaussian surface is actually on the interior of the conductor now. So what is the flux in that region? Well, the flux in that region is going to be 0. Why? Because the net enclosed charge is plus Q and minus Q. So the net enclosed charge is 0. Now that's what you expect inside the conductor. That's the interior of the conductor. There is no electric field, therefore you expect there to be no flux. Okay, and if I go out here with my Gaussian surface, so now it's enclosing everything. Well, now what's the flux? Well, you've got positive and negative. Those two are equal to each other, so they cancel each other. And I've got all of these positive charges out here. So how much positive charge is out here? Well, I know that I've got plus Q. Why? Because the negative Q came here. And then I've got plus whatever was there to begin with. And let's just say whatever was there initially was this big Q. So I've got the original charge that was there in the first place, plus this positive charge that has been induced because of the presence of that positive charge in the center. So the net enclosed charge in this case is positive, so I'm going to have electric field lines that point outward as a result of that. You could go through the same sort of reasoning if this were a neutral sphere. Let me grab my other pen now. This were a neutral sphere and it was hollow. It's a neutral conductor. There's no charge on it now. Now put the positive charge there. The negatives run to the center. Try to get as close as possible to that positive charge. The positives run to the outside. Try and get as far away as they can from that positive charge and distribute themselves uniformly, assuming this is a uniform conductor. Once again, do the same sort of analysis. Gauss's, what's the flux there? What's the flux there? What's the flux around the whole thing? Well, if you have plus Q at the center, then you're going to have minus Q there, and you're going to have plus Q there on the outside. Okay, we've done enough of that.